So the motivation of this next half an hour is not to bore you to death. The idea is, okay, you have an interesting machine learning problem. You get some tools off the shelf. And chances are what worked for other data might not work for your particular problem. So you are going to be facing a lot of choices, such as what model to use, what functions to use, what hyperparameters, how to tune your hyperparameters. And the next half an hour hopefully will provide you with some ideas of how to make those decisions, because we're hoping to bring a connection to you about how all these machine learning terms mean and how they are connected together, and how you can choose why your model is not working for your data and what your data is really telling you. So just a quick overview of what we are going to talk about. So there are roughly 2 sections to this talk. First half, we'll talk about how to understand if your data contains structure or information, if your feature or variables that you're feeding into your model have the signals necessary for you to make meaningful predictions. So the quantifiable way of describing those, a lot of it will rely on the idea of entropy. We'll also talk about dependencies between variables or features, and when you have redundancy information, how to think about dimensionality reduction. The second half will be about making predictions. So now you have features and variables that have interesting signals. How do you make predictions with different machine learning models? So we'll start with graph representation of models, which will be a very useful framework to think about how TensorFlow works and how it's managing and making your life easier by passing around all the data into different operations. We'll talk about quickly what activation functions mean in neural network, but not too deeply. Then we'll talk about loss function, which is the functions that you want to optimize to make sure that you have good prediction powers. And then lastly, we'll touch a little bit on gradient descent, which is really what drives your modeling performance. Okay, so let's start with structure and data. So as I was saying, this talk is not going to be super in-depth. It's meant to provide you with an intuitive understanding of what your data mean and how to choose good parameters. So let's think about a process that's dependent on some input variables such as x1, x2, so on and so forth. And you don't know exactly what's happening within this process, but what you know is that it's going to spit you out some observable y. And let's say you have 2 processes, process A and B, and each of them you make 6 observations. So for A, you make observation of 1, 2, 6, 2, 4, 7, and B, you make observation, and 6 times you see that it's 1, 2, 1, 2, 1, 2. So just intuitively speaking, you might feel that, hey, I feel like I'm a little bit more confident about making a prediction on what the 7th observation might be for B, but not so much for A. So this intuition really captures what structure and data might mean. And there are a lot of different interpretations, and I'm just picking 2 here. So when you think about structure and data, it means that there's a way to compress the information within a data set. For example, for B, you might say, okay, instead of recording individual 1s and individual 2s, I would just say I saw 3 1s and I saw 3 2s. Another way of thinking about it is that if there is structure in data, then given some input, given some prior observations, you have a better confidence of predicting what the next outcome might be. And this can be mathematically characterized by a term you are probably already very familiar with called entropy. So here is the mathematical equation, and you can then compute the entropy of a given process, for example, using Python or using R. And we're not going to belabor that, so we're just going to get some intuitive understanding. So if we say a process has higher entropy, then what we could say is, oh, that's roughly equivalent to saying that if a process has a higher entropy, then I'm not as well able to make predictions for this process. So let's have some examples. So let's have 2 processes side by side. One is a coin flip, and one is a dice roll. So we know those 2 processes very well. We know what the probability distribution for them are. So we could mathematically plug in all the numbers and compute what the entropy is for both. But we could also think about it intuitively. Okay, so higher entropy means that I'm less able to make predictions about this process. Out of a coin flip and out of a dice roll, which one can I make better predictions? So chances are you might feel that, okay, if I predict for coin flip, I just guess head all the time, at least I'll be right half of the time. Whereas if I'm guessing dice roll, I probably will only be right 1/6 of the time. And so that's roughly the idea. So between the two processes, dice roll has a higher entropy. So now consider we still have dice roll. On one side, we have a fair coin on the left. And on the other side, we have a biased coin toss. So let's say in this biased coin toss, we know that 80% of the time it's going to be heads. Now we can, again, intuitively think about, OK, now which process has higher entropy? Now, in this scenario, you're going to be able to make better guesses about what the outcome might be for the biased coin toss. So in this scenario now, you will have higher entropy for the fair coin toss because relatively to a biased coin toss, this one is harder to predict. So far, so good? OK. So we were just talking about what it means for data to have structure in entropy terms. So now let's think about making predictions. So when we make predictions based on some signals we have, there is an inherent natural upper bound to how good our predictions can be, depending on how strong our signals are. If we don't have good signals that can really relate to what the output will be, there's really no algorithm that can tell us what the outcome will be. So to kind of make it into an example, let's think about this process that has only one input variable, x1. And x1 goes into this process that we don't really know much about. And then the output observable is binary, so 0 or 1, or in the plot, positive or negative labels. So let's imagine this scenario that for x1, if x1 is large, you have a really good chance that the output is negative. If x1 is smaller, you have a very good chance that the output is positive. So x1 is a very strong signal that allows you to make predictions about the output y pretty well. Now imagine you have a process that spits out outputs like this, where there's a strong overlap between the distributions of positive and negative labels in terms of their input variables. So in this case, it doesn't matter if you have really good algorithm. Whenever you have kind of a medium value of x1 somewhere in the middle, you're not going to distinguish very well or guess with a high certainty what the output y would be if it would be positive or negative. So this is something to keep in mind when you are tuning your model to make good predictions, is how good your signal is in terms of providing you with information to make realistic predictions. OK, so if information in signal is important, and in features is important, then does it mean that let's keep making observations, let's keep measuring things and stack up different features that we can use, and instead of just having one variable x1, let's have lots of x's, so x1, x2, x3, so on and so forth. Would that make our life easier? So is it the case that the more features we have, the more information we can put into our model? So you probably have encountered this scenario in real life, that when you have more features, that doesn't always mean that your model performance improves, because a lot of time features can carry redundant information when they're dependent with each other. So for example, this is a trivial example where you can see we have two input variables, x1 and x2, and there's a clear linear relationship between these two variables. When that is the case, to characterize it mathematically, we can use the familiar correlation coefficient, which tell us how much two variables are linearly related to each other. So that is nice, but a lot of time in real life, we have two variables that are related to each other, but not linearly. Also, very often, you have probably encountered scenarios where your input, your model takes in categorical variables, so that it doesn't really make sense to think about correlation from a continuous framework. So OK, correlation coefficient doesn't work. I cannot use it to characterize how two variables are dependent. So what do we do? So this is an example of such scenario. You can see that roughly x1 and x2 have some relationships, but it's not exactly a linear relationship. You can see, roughly speaking, when x2 has a small value, x1 is somewhere in the middle of its dynamic range. But you cannot really characterize it with a correlation coefficient. So in this scenario, you could use a more generalizable concept called mutual information, which is based on joint probability distribution between two variables. So the mutual information between two variables will be 0 if the two variables are completely independent from each other. So this is a convenient way for you to be able to capture how much two variables are related to each other without having to make sure that they are linearly dependent. So here is the equation, and this is a discrete version. And mutual information also has a continuous version, or you could also use a discrete version for your continuous variable, just spin them. Okay, so now we've learned that, okay, we can take a lot of input variables, we can feed it into the model, but before we do that, we want to make sure that there is no redundant information among those variables. So is there a convenient way to do this? So for example, if we go back to this scenario that we've seen before, where x1 and x2 have a clear linear dependent relationship, what we can intuitively tell is that x1 and x2 are not the most informative axes. The most informative axis is probably this blue line that goes through the data points that describes their linear dependency. So why do we feel that this green line captures the most information for these two variables? It's typically because this is the axis where the most data variance lies along. And what that means is that most interesting thing happens along this axis. So maybe its signal to noise ratio along this dimension is the highest, and therefore we have a best chance of getting useful signals out of this axis. So the question is then, given x1 and x2, how do we systematically identify meaningful axes like this? So the way you could do it, which is a method that you've already heard in this morning, is called principal component analysis. And here I'll just provide a little bit of intuition of how it works. So let's say you have a feature set. So you have input features, x1, x2, all the way to xm. So in this case, you have m many features. For each of these features, you can have observations. So in this case, you have n many observations. So if you want to relate this matrix with this plot here, then you can say that n is equivalent to the number of plus and minus signs you have on the plot. And the idea is, okay, for each of these, for each pair of these features, you want to figure out what is the covariance between the two features. So just for a moment, only consider two of the features, so x1 and x2. And again, x1 and x2 each have n many samples. So x1 is x11, x12, all the way to x1n, and x2 is x21, x22, all the way to x2n. So now if you want to compute how much related they are to each other, you can calculate their covariance. And you can say, okay, covariance is just the dot product between the two vectors. And I want to emphasize this only works if you have previously standardized x1 and x2 so that their mean is 0. So why does this work? Why does this work if their mean is 0? Because if x1 and x2 have a mean of 0, that means you're going to get a large number when they are varying together and a small number when they are not. So a dot product in this case will work, but only if you have standardized your variables. So now we can generalize to the entire feature vector because we can know that dot product, you can think of it as a matrix multiplication of x1 times the transpose of x2. So if you generalize it to the full feature of x, then you have the covariance vector of x is x times its transpose. So that's kind of dissect what this vector will look like. So the covariance matrix will look like this, where you have diagonal elements and off-diagonal elements. So the diagonal elements are really just a dot product of each individual feature. So the diagonal elements will measure the variance of each feature, xi. And we were just talking about, okay, variance along, we want to keep the dimensions with a lot of variance. So if we want to transform this matrix, the end result is that we want the diagonal elements to have large values and rank them actually in the order of their contribution. For the off-diagonal elements, that measures covariance between two features. And we know that covariance between two elements means that those two features are redundant and correlate together. So when we transform the covariance matrix, we want to do it in a way that the off-diagonal elements are as much close to 0 as possible. So that means when we perform our PCA exercise, what we want to do is we start with a covariance matrix, and we want to make a matrix transformation, which is, you can think of it as axis rotation, so that your resulting matrix will have the property that off-diagonal elements are 0, and the diagonal elements are non-zero and ordered in their strength. And there are many ways to do this. And one of the method is eigenvalue decomposition, which is identifying the eigenvalues and eigenvectors of your covariance matrix, which you can easily do in a lot of different packages. There's also single value decomposition, which is a more generalized method of doing this. OK. Now it's my sanity check to see that I haven't exceeded 15 minutes, but that's not happening, so I'm just going to move along. So is this useful so far? Yes. OK. So now we understand a little bit about our input features, what it means, redundant information. Do we have enough signals to make predictions? So OK, enough of that. Let's talk about making predictions. OK, so in terms of making predictions, we need a model. So one of the simpler models that we are familiar with is a linear model. And that's lower our ambition and say that just think about one feature, x, and comes with two parameters, w1 and two parameters or weights, w1 and w0. And we have a linear model that makes a prediction on what the output y would be. So this is the equation representation of what our linear model will look like. But we can also similarly think about our model in a graphical representation. And this is actually really cool, because what that means is we can draw operations as nodes, and we can draw how our data is transformed by nodes and pass along between nodes that give us the output. So OK, I mean, I'm pretty happy with that equation there. Why are you bothering me with this graphical representation of data? Well, that's because if we think about other different models that's slightly more complex, like this here, like an introductory neural net model, then you can see having a graphical representation really gives you a framework of how to think about all the different operations that's happening to your data. So in this case, this is a simple example of a neural net that has 2 layers, and each layer has 3 nodes. And you have 3 input features. So at each node, all the numbers, all your data is getting transformed by your predefined activation function, different A's. And what the activation does is it transforms and operates on your data, and then pass these data along to the next layer of nodes. And so this makes it a very convenient way of visualizing when you are using a neural net model. How is your data being passed around from operation to operation? So what activation function do you want to use? Well, this is something that you have lots of choice on. So you could use a linear function, which means that for each node, A1, A2, so on and so forth, it's just making a linear operation for the input data. There are a lot of other activation functions that you can choose. For example, sigmoid, max out, and also ReLU. So OK, there are so many options. What should you do? Well, if you're in doubt, currently, right now, ReLU is really popular. So maybe go with a popular choice. OK, so now you pass all your data into these activation functions and pass the data through different layers. Now in the end, you have an output prediction. So unless you have chosen your activation functions very strictly, chances are your output y hat, your prediction is going to be a real number between -infinity and +infinity. That might not be applicable if you are trying to make a binary prediction of either 0 or 1. If that's the case, then all you have to do is just add a sigmoid function on top of your prediction, very similar to what you do in logistic regression, which will transform your y from -infinity to infinity to 0 and 1. If you're making a categorical prediction, which means that your prediction is not going to be a continuous number, it's also not going to be either 0 or 1, but it's going to be one of several classes, then what you will do is you take your raw output and then apply softmax function on top of it. And this is really convenient because once you do that, there is automatic normalization condition that is obeyed. Okay, so now you've made your prediction. You have your, let me backtrack a little bit. So so far you have all your features, you have all your variables, you have verified that there's interesting signals in your features. You feed it through a model, you chose your activation function, you made your predictions, and you impose sigmoid or softmax function on top of your prediction based on what kind of prediction you're trying to make. Now the question is, okay, your model is going to have all these parameters or weights, wi, which you have to tune to make your model perform as good as possible. How do you pick these weights? So usually what you will do is, okay, if you want to pick good weights, this turns into an optimization problem. So what do you want to optimize on? Well, you want to make as little mistakes as possible. So typically what you would do is define a loss function, which characterizes and quantifies how much mistakes your model is making. And again, this is something you have lots of options. So typical loss functions that you might have seen is called L1 or L2. They are very similar to each other. L1 is just the sum of absolute differences between your prediction and the actual observable. L2 is a square sum. So this will be applicable if you're making predictions for continuous output. What about if you're making binary output or categorical outcomes? So in that case, you are not comparing your raw output, which is a number, to an observation, which is another number. In this case, you are comparing your prediction, which is a probability distribution, to an observed probability distribution. So you're not making comparison between numbers anymore. You're making comparison between probability distributions. When that's the case, what you could do is you use this concept called cross entropy to allow you to compare how good your predicted probability distribution is compared to the true probability distribution based on observations. And if you have a logistic regression, a binary situation, then this is what the equation will look like. And you can see there's a lot of logs in there, so that's why it's also commonly known as the log loss. Okay, so last 4 minutes, we'll talk about gradient descent. Unfortunately, this is probably also the most important thing. Okay, so you have your loss function and you have your wi parameters. How do you iteratively pick better and better parameters so your loss gets smaller and smaller? So for now, let's just think about one parameter, w0. So of course, your loss function is going to be dependent on your choice of w0. And so what you can do is say, okay, I'm going to start with just any w0. And then I'm going to pick a new w0 based on how much I can decrease the value of the loss function. So if we think about it as kind of a curve for what the loss function look like, dependent on w0, what we're doing is basically computing the local gradient and then figuring out which direction our next new w0 should be, and then take a step in that direction. And so alpha here is typically known as the learning rate, characterize how big your step is going to be. And so in this picture, right away, you have this intuitive understanding of, okay, if my learning rate is very small, that means I'm going to have to take many, many steps until I find a w0 that minimizes my loss function. That's maybe takes too long. However, if my alpha, my learning rate is too large, then what could happen is I'm going to move along in the direction very quickly. But once I get close to a minimum L, I'm going to be bouncing around in the valley. So there's definitely some art in choosing what the alpha could be. And you can use a lot of nice methods such as decaying learning rate. In reality, we don't just have one w0. Typically, you have lots and lots of parameters to tune. So in this case, now we're considering just a little bit higher dimensionality where we have w0 and w1. So as you can see, the kind of the loss function landscape is now starting to becoming a bit crazy. In real life, you typically will have more than just two parameters. So your loss space is going to be in really high dimensional space. And I'm happy to kind of like nerd out about it if you want to talk to me after that. Okay, just to wrap up. So if we think about having to compute gradient descent, let's go back to this old, to this neural net that we just saw and simplify it even a little bit further to just 2 layers and each layer having 1 node. So in this scenario, what happens is that you have your input x along with your parameter w0. You pass it through the first activation function that's called f. And then the output of that function, you feed it into a second layer, which is an activation function g, and then you spit out your prediction. So this is the graphical representation, and this is actually equivalent to what you might have seen in your introductory calculus class as g of f of x. And in the end, what you want is compute the gradient of your loss function with respect to w0. And this might be really tedious to compute until you really realize you have this nice trick called chain rule, such that you can express this derivative as the multiplication of different local derivatives. And why is this nice is because instead of having to compute change of L as a function of W0, as you're passing through all these different nodes, you can compute locally what is the how is G changing respective to F, and how is F changing in respective to W0. And if you want to compute the gradient, what you can do is after you make your prediction, just go back and pick up those values that you have computed previously, and then get your overall gradient like that. So this is a very, very superficial way of trying to understand back propagation. Okay, so that's it. And there's still a lot of things that we didn't really talk at all in depth. And I also have some resources that I found to be really, really cool that I will share with you. And I think the best thing in here that might be most relevant for this workshop is this TensorFlow playground. And so we were talking about getting some intuition about how to play and choose your model hyperparameters. And so this is an interface that allows you to do exactly just that and get some intuitions about, for example, what happens when you increase learning rate, what happens when you choose different activation functions, so on and so forth. Okay, so I intended on leaving time for question, but yeah. No, so let me repeat the question. Are these slides in the repo? No, because these slides, I just made them like this morning. Yes. Sorry, could you say? Oh, yeah, of course, yes. So I hope this was helpful. Okay, so now David will take you deeper into TensorFlow, and you'll get to try your hands out on tuning all your hyperparameters. Have fun.
Okay, hey guys, we have a short feedback form. So if you, in case you have to take off early, we'll show the link right now. And we'll take a short 5-minute break before David presents. So if you need to use the restroom or anything, and also 2 things, our Slack invite link should be up now. So we'll post that up as well. So if you're not part of the Slack group yet and you had issues signing up, I contacted Slack, so they increase the limit so we can get more invites in. And also Jen's presentation, we'll send out the link after as well.
Not yet, but
yeah, okay.
I can maybe turn it into
Okay. Okay, yeah, and here's the feedback form. And we'll share Jen's presentation afterwards on GitHub. Yeah, do you want to have another announcement? Oh. Okay. Okay, cool. Okay, so yeah, feel free to take a 5-minute break if you need to use the restroom or anything.
I want to encourage them. If you fill out the form, we're more likely to be able to get funding to do things like this again. So please do that. Thanks.
Yes.
So you created a new instance, so you try to, and you got it. So I think it's kind of random, but most of the time you don't get it. And the problem is if people keep trying a lot, it's increasing. I message Jeremy Freeman. I think we should encourage people to work locally if they can. Anybody who is able to work locally, they should do it locally. Maybe you can try to sort out other people who are not able to.
Can I just follow on GitHub? Is that okay? They can't run the stuff. But
Yeah, they can.
Okay.
Yeah, they can read only with a book. Maybe that's the way to do it.
yeah, I think we should probably.
There's my
So we know that.
People who register. Oh, but I thought people registered.
They were like,
So I
yeah,
message
what they did. So you just send it to us.
Yeah, I can send it to you.
Yeah, and they just
I don't think so. She wants to, yeah. Yeah, where is Olivia? She mentioned she's part of Google Cloud. Did she? I don't remember if she mentioned.
Oh, I saw, no, not really, but I know that people make it close. We're like, okay, so you learn something else, so we can bring that.
Oh, not this session. No. Yeah.
Oh, I will.
But did you,
I'll use education.
I have to say to directors.
okay. Correct. I guess so. Like if most people are able to, this group or a different? Oh wait, sorry, this one. Oh no, that's. Oh, I did. Did I post on the wrong Meetup group? Oh no. Yeah, maybe I didn't post it. I thought I posted this Meetup. I just need to post last time. Maybe I didn't. Okay, interesting. Oh, maybe he meant on the women in machine learning.
Google Cloud, let's see, Google Cloud will require credit card number, even though it's not charged. So that's an option. And then there's that other weird place I mentioned. We put some in there, the two cloud options. Yeah. Choose. Choose. And there's this. Oh, I just have it listed, but there's another one.
Should you want to do this announcement then, and I can you share your screen? Okay, cool. And then we can ask people to do that. I think that would be good. Okay, so if you get on the yeah.
If not, we can just share.
I think you just need to.
Oh, I just need to get on the yeah.
Yeah, it's weird.
What was the other one? Cloud9. Yeah, that's the other one. So we can do it through this. There's a blog that will tell you how. This will be really useful though. Here we go.
The GCP one. The GCP going platform one that she set up.
Yeah, I'm going to tell you about that.
Yeah, that's probably the
Do
next
the
one.
lab.
Yeah.
Actually, I might go through it with them because it's actually something to get to. I think.
Okay. Yeah.
Yeah. Oh, can you press it? Yeah. Maybe it's before me now. Oh, screen sharing, yeah.
Yeah.
I get it.
Should we save? Oh, we have to click that too. Should we record? It's recording. We can pause it. Oh, but no, I think we did. What is it? We'll have to cut this out.
Sorry for the hold up there, guys. So real quick. Hey, so I just want to mention some installation stuff for TensorFlow because it'd be awesome, right, if everyone could interactively participate with the notebooks. So we're trying to. We had one option, and it's with this the binder, mybinder.org, and it seems to be a little just janky right now. It's okay. It's a great service that someone is providing to us, but for some reason it's just for the TensorFlow stuff, I think it's quite difficult just because TensorFlow is pretty complicated in general to install. So given that, we highly recommend like some cloud options. So the first one would be the Google Cloud Platform, and the link is on, I guess this is the intro to sklearn GitHub repo. So it's at the end. There's other install options, and so there's a link to Google Cloud Platform. So in Google Cloud Platform, they made a product called Data Lab. Data Lab is actually a really nice Jupyter notebook system. And since it's Google, it already has TensorFlow on it. So yes, we should have told you about that at the beginning. So it's one of those services, though, you do have to enter your credit card in. Unfortunately, yeah, I mean, Microsoft does that too with Azure. So we're all the same. We just copy each other. So anyway, but it won't, charge you anything. It just wants that. But once you get into it, you'll navigate to Data Lab. So I can, if you want, go through that real quick.
Okay, sure. Yeah.
Would that be, who doesn't want me to show you real quick Data Lab? There's a mass majority, then I won't do it. No one. Okay, you guys want to see it? Okay. Yeah, I think that's actually like a really good option, right? Because it'll probably be the latest updates and all that, since it's directly from the Google people, the Google Cloud Platform people. Okay, so this is really unfair to you guys because I already have it set up. Trying to think if I can sign out. Yeah. Oh, it's going to sign me out of the Hangout too, isn't it? Okay, so that is not going to work for me. Hold on. Oh, shoot. I need Catherine. Catherine! Can so I logged out of my Google account. I guess it's, and so it hung up. Okay, but it's still recording. No, I'm not. It's hung up because I'm not logged in anymore. I don't think I can do the Data Lab stuff because I already have a Data Lab account. I think we should just move on. Because I can't. I'm not going to be able to like log out and set it up and then log back in. So yeah. Because it's just presenting us, right? And then I can join. And I got that. I have to cut out all of this. And then pin me. Okay, sorry about that, guys. I work at Microsoft, so I don't know anything about logging in and logging out of Google accounts. So I do have this already set up. It's actually not terribly difficult, but what you'll do is you'll just go to your, you can Google Cloud Platform, and you'll want to look for Data Lab links as an option. And you might have to search a little bit, but once you do that, it'll look like this. So you'll have to do two things. I think you have to like add Data Lab as like an option for your Google Cloud Platform. It's all free, but you have to add that as an option like you usually do with, embedding Google stuff. And then you'll have to create a new project in Google Cloud Platform itself, right? So once you have that, you create a new project. Oh, do you know how to do it? It'll pay for it, or like you'll have to pay for it, the background classes. Oh, okay. So thank you. Yeah. So if you're, yeah. Yeah, so I don't know if you guys heard that, but basically there's tons of credit you get when you first start this. And so don't worry about getting, overage for that at all today. So, and we're not starting up any, I don't believe we're necessarily, well, okay. Well, I'll do some research and come back to you at the end to see if you need to shut down anything. But I have not been billed, as you can see. And I've had this running for a while, like month or so. So my credits must, well, I haven't really used it for anything but the Jupyter Notebook. So it has tons of credits for you guys for free. So once you get a project, I think how do I do this? I'm having some problems with this. I'm sorry.
The Binder team said it should be working now. Like I tried, so.
It's working. Oh, I don't know what it is. This is bad. Okay, this is really bad. I'm like gonna not do. What should I do? I forgot.
Someone was saying that you can go to datalab.cloud.google.com.
That's what it is.
Datalab.
Oh, Google.
It's just datalab. I mean, he gave me the URL. Datalab.cloud. Yeah. And then you just sign it.
Oh, I must be like some sort of crazy. Oh, you know what? That's what I did. Oh, thank you so much. Okay, this is kind of a learning curve for me because I've done this only once. So once you've signed up for Google Cloud Platform, I'll put this up on the Slack site, or actually I'll put this up in somewhere everyone can see it. But so once you have that signed up for Google Cloud Platform, you can go to datalab.cloud.google.com, and then basically I will select a project. Remember I said you need to start a project at least in the platform part, and then I just select a project for it to kind of live in a container, and I hit deploy. So that will set up in a bit a Jupyter Notebook system for me. Also, I just heard that the binder link is working again, but this would probably be the best option, I'd say, for having the latest and greatest TensorFlow, and also the bandwidth, is reliable for the Google Cloud Platform and Data Lab. So we just wanted to make sure you guys knew that option and all the proper places to go for that, even though, I wasn't quite sure. So it's a team effort. I'm going to turn it over now. Hopefully you guys have something that's working. So thank you.
Oh yes, I need to go to calendar and log into the. This one. Which one? And then I want to go to share. Maybe, no, I want this one.
Entire screen or just
Just, well, just Chrome. But that's Bash. It's in the background.
Oh.
So. I'm gonna go. Oops. There. Okay. So now let's get started and learn some TensorFlow. And I'm going to start this tutorial off, though, the way this is based. Yeah, I'm going to go through a little bit about pre-processing and some pandas, setting up the data. And then after that, going to go into Skflow, which is kind of like a soft introduction to TensorFlow. And then finish off with TensorFlow at the end. So this file, it's the wine quality. This notebook, it's in the directory. So if you look in the repo, there's a directory called wine quality, and inside there is where the notebook is. So I chose this database, this data set from the UC Irvine Machine Learning Repository. This is a great place. I provide the link here. It's a great place if you want to go and find a data set to play with. And it's one of a really good way to learn machine learning and learn data science is to go and find some real data sets out there. And that's what this data set is from. And this data set was based on chemical analysis of wine. Some researchers did this analysis, and then the wine was rated in terms of the quality of the wine from 1 to 10. I'm going to only take a subset of that, and we'll see that later. So this is like a categorical analysis of wine. So here, first thing I'm going to do is import the necessary libraries. And now I'm going to load the data. I'm going to load the data using pandas. This is how you load data. This is the name of the CSV file. And it's going to be loaded into a pandas data frame. As Micheline was mentioning this morning, a data frame is a way to store data. You can kind of think about it like Excel. It's a way to put data into like an Excel spreadsheet. You can manipulate data in a data frame in pandas, similar to how you can do it with Excel. Now, one of the really good things to do when you're faced with a data set is you want to understand, well, what does the data set look like? You don't want to just go and start modeling right away. You want to understand what does it look like? What do I want to get out of it? And then come up with a strategy. What's the best strategy for how to model this data? So there's 3 different commands. Micheline presented some of these in the morning, but there's 3 different commands in pandas to be able to see what the data set looks like. One is called head. So what this does is this just lists the first 5 rows of the data frame. It's a good way to be able to see what are the column names and what does the data look like? What does the few of the rows of the data look like? So here you'll notice there's different chemical properties of the data set. And here, can anyone looking at this, does anyone have any idea what are the features or which column might be used for the labels, the target? Quality, exactly. So quality here, the last column, this is the column that we're going to use to the categorical column that we're going to be used to classify the type of the wine, whether it's considered good wine or bad wine. So the smaller the value, the worse the wine is. Higher the value, the better the quality. And then the rest here, these are all the other features. And these are features from the chemical analysis of the wine. Another thing you can use is called describe. So here, the describe shows various metrics for the different categories, the different features. And I'm using here this .t. This is to transform. So basically what it's doing is just tipping this table on its side. So it's putting the columns as rows, and then it's putting the metrics at the top. I like this better because it's kind of an easier way to look at it, where you have the metrics on the top and you can just read off on the left the different features. Especially if you have a whole lot of features or a whole lot of columns in your data set, then it might be difficult to be able, might not fit all on the screen, but these columns will. So it's another reason I like that. Another thing you can use is called info. So what info does in this case is it just lists, again, sort of like describe, except in this case you're listing the different features, but it's telling you how many features there are, how big the columns are, how big that data set is, and it's telling you the data type as well. So this is really good. One good thing about this is, for example, if you looked at the head up here, you would see that they're just numbers. But what if somebody entered a value wrong and they entered a string instead of a number? Well, in that case, you would notice something down here. It wouldn't show up as float 64. It might say object. So that might be a flag to say, oh, maybe there's something wrong with the data. So it's a good way, this way, to be able to look at the features and get an idea if those data types for those features make sense. And that's part of the cleaning process when you're doing data science. So if you looking at the features, what's the dimensionality? How many, in other words, how many features are there? So basically, 11 exactly. So basically, you're just counting the columns, all the columns except quality. And quality is already discussed. That's the label column. Okay, so that's a tabular way to investigate the data. Well, it's another really powerful thing to do, and something that a lot of people are visual. And I'm a visual person, and I really like to be able to see the data. In that case, it's good to make some plots, to be able to look at how are the features related to each other. And one really good way to do that is to use something called a scatter plot. And Seaborn has something called pair plot, where you can make a scatter plot matrix. So what that is you're just plotting one feature for another feature for all of the features in the data set. So if you have, and I'll show you an example. So let's import Seaborn. And now make a scatter plot. This takes a little while because you're making a lot of different plots. So it's the idea here. It's just about to show. This is a really good way to visually see as scatter plots and look at all of the data and look at all this whole matrix of different scatter plots, which I'm showing here. And you can see if you go down like volatile acidity, you can go up and you can see how does volatile acidity compare with alcohol content or sulfates or pH. And you can see how they're related. You'll notice here that it's very distinct values. That's the quality column. So a quality has specific values, integer values, which is why it looks like that. And you'll notice in some places as well where it looks like there's quite a correlation between those values. That's an example of colinearity. So that's what was what Jen was talking about. These features have, because they're collinear, they're redundant in the model. They're both giving the same amount of information for the model, so it doesn't make sense to include both of those features when you're modeling. And this is a good way to visually be able to see, to identify whether there's collinearity or not. Now you'll notice this along this diagonal here, there are histograms. This is where you're plotting the same feature versus itself. So it's just showing the distribution of that feature for the data set. Okay. So that's a visual way to see what your data set looks like. But another thing also when you're modeling, you might not want to, there's various ways to clean the data, but one way you might want to consider is, well, I mentioned about collinearity and maybe throwing out a feature for that. Or another thing is to look for values that might be pulling your model in the wrong direction. That might be like outliers. It might be values that have extreme values. So for that, I defined a function to look for outliers. Now here I plot some outliers. Here what I'm plotting is just a subpart of the scatterplot matrix, just considering total sulfur dioxide and sulfates. And you'll see these two values here. They look like they deviate quite a lot from the mean. And so in that case, we might want to throw those values out. We might not want to consider them. And here I can just do a describe on just those values as well. And so now in order to look for outliers, I define the outliers as being a certain number of standard deviations away from the mean. So I'm defining a function here in Python, which it takes a data frame, it takes the threshold, which is a number of standard deviations away from the mean, and what columns I want. In this case, I'm considering the whole data frame except the quality row, all the features, but you might not necessarily want to do that. Let's define that function. And I'm going to list what the columns are. I'm going to, here what I'm doing is I'm taking the columns of the data frame and I'm transferring them, changing them into a list. So now that list is something I can pass to my function. And here I define a threshold. Oh, I should say too, something I didn't point out. I'm not actually going to throw out those values. I'm setting the outliers equal to the mean of the distribution. So just pulling them into the center. Okay, and here I'm chose a value of 5 for the threshold. So now I'm going to make a copy of the data frame. And since I don't want to interact with the original data frame, and I'm only going to use all of the columns except the quality, the label columns. And I'm going to set that to a new data frame and run it through. And now I have my new data frame with outliers removed. The values have been changed. And now we can produce another scatterplot matrix, except with the adjusted values where I've removed the outliers. So as this is processing, are there any questions so far?
So under what circumstances you want
It's not always. There may be some cases where you might have an outlier that's maybe scientifically or significant. It could be a value that maybe it's like it's a real value and it's something that maybe you want to get more data to sample that. But in case for like a bad outlier is just maybe if it's a bad measurement or something went wrong with the experiment or something like that, that'd be a bad value. So you also, it's really good to understand the data and kind of consider whether you think that outlier, before you throw it out to whether you think that outlier is actually something significant and it's something that's important to consider when you're doing your modeling.
Isn't that very difficult to make a guess from?
Yeah, it is. Right, exactly. In this case, I'm showing this is more in the case where you're considering a data set where you know anything that's certain standard deviations away from the mean, that those are bad. But it's really important though to make sure that, like in this case, it's okay. But if you're, but when in just for the modeling purposes in this case, but in maybe in other cases, you want to be a little bit careful before you just throw them out. Make sure you understand the data really well. Yes.
Other side of this opening, remove the outliers from.
Right, you should remove, right, you should remove plus and minus. Let's see, I think I did. Yeah, let me look at that. That may be something that I missed there. But yeah, it should be, that should be like plus or minus into the absolute value. Okay, thanks.
And if you're unsure, you typically train the model with and without and see what the accuracy turns out to be. So sometimes you're right, you don't know whether it is actually an outlier in your data set or whether it's an error in measurement. Right, so you train your model with them in place, without in place, and then measure accuracy on an actual real life data set and see which is more accurate. If it's way off, then you kind of know that those outliers are actually errors in measurement than actual data.
Okay, thanks. So let's take a look at two scatter plots with and without outliers. And you can just see the difference here between these two data sets. Here's the one that has the outliers, and here's the one at the bottom that does not. And so I encourage you to you can play with the threshold, try different values, and see how that changes the threshold as well. Yes.
Question. So would it make sense when you're plotting these to plot normalized values just so that the scales are not vastly different across features, or would you just plot them in the original scale? Like what's your like different features have different ranges, right? Like
right.
The pH obviously has one range versus sulfates have a totally different range.
Yeah, exactly. It's a good question. I think in that case, if you normalize it, I think that would help to be able to see the shape of the distribution without these extremes in values. I chose 5 because I thought it was that's a pretty large value, but you can it was more just kind of like a personal selection, but you can choose maybe other values might make more sense. So oftentimes you can consider values like at least 2 standard deviations away. But in this case, I considered things that were really extreme, and so that's where I chose 5, something that was way far from the mean. Okay. So now let's get into the categorical analysis. So now the data is, in this case, in this data set, it has this data frame, the quality ranges from 3 to 8. So it doesn't include really bad wine nor really good wine. But for the modeling, just to make it easier, I decided to bin the data into 3 different bins and say whether it was good wine, bad wine, or average wine. And so that when you would do the model fit, it wouldn't be fitting to many different categories. It'd be fitting to maybe 3 different categories. So here's the different qualities. And now you could using something called cut in pandas and assigning it to a new feature here called category, you could bin the data and label it by bad, average, and good. So it's basically just cutting up the data in terms of bins of quality. And now using Seaborn, I can produce another scatter plot matrix, except now color code the different values in terms of their different categories: good, bad, and average. Okay, so now we can look, and you can see that the bad values are in blue, the average values are in green, and the good values are in red. And you'll see that for these values, you'll see that some of the bad and average overlap. So that might be if you want to just produce, in this case, this goal was to be able to produce a model to give an example of doing categorical modeling. So I wanted to be able to come up with two distinct distributions that you can see. But you'll notice that there's a lot of overlap between the different qualities. So here you can see this is showing the metrics for the different features, for the mean and standard deviation by category, and by category bad, average, and good. So this is using something called group by. This is another routine in pandas, which is a good way if you want to just compare metrics about the different features in different sub-features, in this case, bad, average, and good for the different features in the data set. Okay, so now, as I mentioned, it seemed like there was some overlap between the average and the bad values. So I thought, let's just consider the good values and the bad values, and just model the data that way to be able to classify whether the wine is good or whether the wine is bad. And so that's what I'm doing here. I'm only selecting these two. And I'm going to bin the data again. And now I can make another scatter plot matrix. But in this case, just considering the bad values and the good values. Okay. So now it looks a little clearer where you can see in some cases, some instances, where there's clearly two different distributions between the good and the bad, two different clusters. Down here. And now here I'm showing just the good values and the bad values, and there are various metrics for them as well. And so here I have a question. If you look at these features, can you identify any features that you think might be related to each other? Even just looking at their names and thinking back to high school chemistry, what what features might be related to each other could be correlated with each other and might be problematic for modeling. Exactly. So pH and citric acid, anything with that, with acid, those something maybe you wouldn't want to consider both of them when you do the modeling. Now, another way to be able to look at the data, instead of doing a pair plot, scatter plot matrix, is a heat map. What this heat map is showing is this is showing the correlation between the different between all of the features. So here, if there's a negative correlation, strong negative correlation, it will look blue. There's a strong positive correlation, it will look red. If there's no correlation or very little correlation, it will look white or very pale. So this is a good way to get a quick idea of what the correlation are between the different features. But disadvantage of the heat map is it doesn't have quite the detail that a scatter plot matrix has, where you really can see the different features. And you'll see here so here you can see some features that have a strong correlation and anti-correlation with each other. Okay. Well, I think we can take like a 10-minute break. I could take a few questions on this part. The next part's going to go into the modeling. So if there are any questions, I could take that now, or let's take a 10-minute break and then we can start again in a few minutes. Get up, stretch your legs, get out some water or whatever. Hey, yeah.
Really nice. So I'm pretty new to the notebook, so sometimes the data frame I have so many features.
Okay.
I want to print the list of the features.
Okay.
But if the feature is like over 100, it only give me some of them and omit.
Oh, so it doesn't.
Is there a way to just visit it?
There's something called, I think, called toString, where it will show. But I think in this, if you do it like this, I mean, I presume is it doing. So if you just look at the columns, and then do a dot T, maybe you can turn the columns this way so it looks like that. So you just see the features.
Yeah.
So if you just look at, if you do like a. And the quick one is thinking if you do dot head n equals 1, so just there's the first row, then afterwards dot capital T, we'll turn it. Maybe it'll show it this way, but I don't.
Yeah. I'll
so
try.
I'll play around with
this
thought,
describe thought here. This trick is really good.
Right.
First time
Yeah.
I saw this.
Right. I learned about that
Very nice.
last fall, so it's great. So.
Nice. I'm looking forward to the TensorFlow.
Yeah. Okay. Cool. Yeah. Did you download the whole repo? Right, or if you could just download, this file into the directory where you have the notebook, you should be able to.
most collinear between the two variables based on this table, and you're like
Well, so in that case, I was mostly just asking like an academic question about just thinking chemically, how are they related?
Got it. That makes more sense. I'm looking
Right
at the data.
now.
I'm like, it doesn't make any sense.
Like if you just think about not even know anything about the numbers, you just think, well, but about these features. Yeah.
Really good.
Good. Okay, thank you. Uh-huh.
Big data. So when I do these correlations, find correlation between different features, is there, in your experience, a certain threshold you use, like if they feature above, let's say 90%, some value, then you remove one.
Right. That is a good question. I think for that, a lot of things I haven't done haven't considered that question specifically, but I think it's, I mean, a lot of it kind of depends on your data, depends on whether it's an outlier. I mean, whether it's an outlier or not. Oftentimes, like when you do like Gaussian distribution, if the value itself is if it's anything greater than 2 or 3 standard deviations, you consider an outlier. But a lot of it also just depends on the data. It depends on the data, and it depends on whether.
In the end, you should about your correlation.
Oh, I see.
Looking at
Okay.
correlation between different features, right?
Okay.
So my understanding is you're looking at correlations of
Right.
you can reduce the feature space.
Yeah.
You can remove some features which are highly correlated.
Right.
But what threshold
Oh, I see.
you
Threshold
use?
of that, matter that one.
Because
Okay,
there, I
threshold,
mean,
yeah.
yeah, subject. If I use 90%,
Right.
why not 85? Or if I use 75, they say that's too low.
Right,
It should
yeah.
go high. So how do you, in general, because you don't know,
Right.
how do you in practice what threshold you use?
I'm so pretty new to that. I don't know. I mean that, but I think it's. I mean it's probably depends on. You can. I mean, one thing you can do is assign different thresholds, and then model your data and see how it affects it, and do it, keeping in certain. There's a lot. A lot of that when you're modeling. You come up with certain criteria and you think, okay, well, this is the criteria I'm going to use to be able to throw out a different feature. But maybe if you keep in your models are better or reliable.
Try
It kind of
different
depends.
versions of the model and then see the
Different
accuracy on the test.
Yeah, exactly. Like try different. You can do like use all the features, or just 3 features, or 1 feature, or different. That's what you can be able to really see. I mean, you could do when if you're considering 2 features are related to each other, you could. But you're not sure whether you want to draw one or not. You could keep them in, and then you could model it both of them, and then model like one not the other, and the other not the first one, and then see how their models compare, and then from that you can make a decision whether it makes sense.
So as I keep trying to do this, I can learn the same thing on bar reviews yesterday. And other questions is like when we're doing some of these models, you're not expecting the data to be normally distributed.
No, I mean not right now necessarily. It might be skewed.
So here's my thing is like I work in insurance, so that's my regular job. And then let's say we have 1,000 policies. There's going to be 900 people where we're not going to see any claim at all. Okay. So there'll be you know, like crazy policies where we'll pay $500 done. Majority of those would be anywhere from say $10,000 to $50,000. Handful like three, right? That's going to be $1 million. I mean, so it's yeah, so it's like we don't have any claims to kind of go like a normal excavation, so then all of them, and then I can't really prove those out either because those are not necessarily outliers. I mean, in a way, those are, but the thing is that it happens often to kind of sort out.
Well, in that case, outliers qualify or still like that.
So I usually try to use the logistic regression to come up with is it going to be over 50,000 or like so that way at least I'm not doing it. Thank you.
So I think I just switched to housekeeping.
All right. Hold on.
Well, I was just 10 minutes, but so it's been about 10
Okay, we're gonna get started soon. So if you could take a seat, and we'll get started very soon. Okay, so let's just plug
Thanks for letting me.
Yeah, sorry, I forgot that you had mentioned that, and then I remembered. Oh yeah.
Yeah, you put it
You
together.
sent me an email a while back. And I was
I know,
Like, okay, so
totally.
things like.
Right
Yeah.
on. Yeah, this is
Okay.
great, by the way.
Oh, glad
The
you're.
quality of the talks is awesome. Good speakers. All right, let me get my. What do you guys want me to mention? Specifically, just the meetup and maybe the workshop. Okay.
Yeah, just like about the workshop and meetup, and then maybe next time we're gonna do not have this installation issue. We'll be having it
Right
on
on.
meetup.
Okay. Sweet, man.
Yeah.
It's like a command center back here.
Yes.
How do you guys keep track of all this?
If this doesn't work, then maybe I have to actually. I just don't want to like mess up David's environment.
Yeah, I mean,
I guess this will work. Okay. Spark and TensorFlow.
Which company do you work for?
Okay, let's go back to this.
We use heavily TensorFlow.
Sorry, I just.
When did you start using TensorFlow?
Almost a year ago. Before that, I'm using scikit-learn.
Yeah.
And then it's had a lot of issues, and I don't want to go back to R.
Hi everyone. So we're gonna get started here. So Chris here is organizer of the Advanced Spark and TensorFlow meetup, so he'll give a quick introduction about the meetup group.
Hey there, guys. Thanks for having me. I'm signed up for the women's like meetup, which is how I got in here. So I probably shouldn't reveal my secret, but yeah. So thanks, Kendall. I just want to mention this meetup. This was the Advanced Spark meetup about 3 months ago. I had tacked on TensorFlow. I read the TensorFlow paper. There's a lot of like good principles behind it. Like distributed systems principles. Wanted to mention too, in the vein of this like type of workshop thing, there's one coming up on June 4th. This is a paid workshop. If you guys shoot me an email, I'll get everyone like super duper discount, whatever. We're gonna have about 100 people, probably 120 people. We did this about a month ago. We created a huge Spark cluster. We're gonna try to do the same with like TensorFlow cluster. So it was all 100 people connecting to one master and then running jobs. So we have that coming up. What else? Oh, and then, I'm going to sponsor next session for this. So like the way that I do the workshops is I just give everyone a GCE like instance with Docker like fully installed that has all this stuff running. So that like we're not going to spend like the whole morning, hour and a half getting things set up. So it's just I give you guys an IP. You need like SSH and a browser, and we just start coding. So. June 4th, and then there's another one August 6th, and then next time you guys organize this, I'll pay for it. So, thanks.
Okay, thanks, Chris. And back to David.
So. Okay, let's get on to TensorFlow, and but we're going to start off with Skflow, which uses TensorFlow. But Skflow, this question.
Yes. I have actually two questions before we go to the Skflow. When previous one, when we look at the heat map and we look at the correlation, so is there a certain when you decide to go down, like 80% correlation, 80, 90, is there a number to it? Or anything when we decide which one of those is not
right, like if there's a okay.
And the second one is like I've noticed that when sometimes like we get out and because of colinearity, but then all of a sudden my cluster is not where we did the next bump.
Right, those are two good questions. But the first question was how to, like, if you're looking at this, how do you decide a threshold for the correlation, whether you want to throw out a value or not, depending on how much of a correlation there is or not. In that case, it probably depends on your data, sort of like the outlier correlation. So maybe very kind of individualistic to what the data is. If you see in this case, there are areas where it seems most of the values aren't that correlated, but there's some cases where there's quite a distinct correlation between them. In that case, you may just look at those values, and from that, where there's a really distinct correlation, and decide, okay, you're going to throw out those values. And another thing that you might want to do as well is when you're doing modeling is consider if you have values that are really highly correlated with each other, or ones that you're not quite sure. Maybe you pick a threshold that's and some values seem like they're close to the threshold. You could model your data with both of those values, and then take one value out and model the data, or take the other value out and model the data and just see how it affects your models. So yeah, and you could see, I think the question was about the R² value. So you could kind of see how with or without those features, how it affects your model quality. So, okay. So now I'm going to go on to Skflow. Skflow it's similar to, uses routines and that are similar to routines that you might see in scikit-learn, but it's in the background it's calling TensorFlow routines. So it's a way, if you come from a background where you know a lot about scikit-learn, you might, in that case, you might want to start with this to be able to kind of transition, a software transition to what TensorFlow is doing. So here, Skflow, it's now part of the TensorFlow library. So now when you import it this way. It used to be separate, but now it's considered part of it. So now I'm going to separate the values, kind of like what Micheline did in the morning. Separate the values into the features data set and the training data set. The features and labels, and then split those into the training and test sets. So first of all, let's divide this, get the labels. So we're going to get from the categorical variables. And in this case, to start off with, let's just try one feature. We'll see if this one feature, total sulfur dioxide. You could pick anything, but in this case, I just thought, let's see what happens just if we pick total sulfur dioxide and see if from that we can be able to infer whether the value is if it's good or bad wine. I'm going to do that. And now I'm going to use this train test split, like what Micheline did, and divide it into the training and test sets for the features and for the training test sets for the labels. And now I'm going to use this categorical processor. So what this is doing in Skflow is this is taking the values and categories. They're strings. It's bad or good. Well, the TensorFlow doesn't really understand strings very well. You need to give them something it understands. In this case, numbers. So that's what this is doing. Is it's basically saying whether if it's a good value, it's going to get assigned a number like 1, and if it's a bad value, assigned 0. So that's what's happening here. So it's only for the labels, because that's all. The features are fine. They're already numbers. And now we can list the different classes. So we can save the number of classes to a variable, and we can print the number of classes. Now you'll notice something peculiar here. I was considering values which are bad or good. Well, the way this categorical processor works, it also is considering it has an unknown token. So it says that there's 3 when there's actually 2. So just the way it works. So now we're going to define our model. In this case, I'm using logistic regression. And I'm going to set up the TensorFlow estimator. And so here it takes the number of classes, and it takes the learning rate. This is, as Jen was talking about, this is how fast you want the model to learn. If it's learning, it's going to learn too fast, then in that case you might fly by the best value. Or if it's learning too slow, it might just take forever. So the learning rate is something when you're modeling, really, it's a value to play around with when you're modeling, to try to figure out, it's a parameter that you can change.
What's the range for the learning rates?
0 to 1. 0 to 1. So Okay, so now that I've done that and set up the estimator, now I can run the model. So I'm going to run it. I'm going to fit the training with the training data with the training labels using classifier. And so it's going to go through. It throws an error, but this has to do with different versions of Python. But it's still it's throwing out. So here it's iteratively going through the model. And this is it listed different. It takes a lot of default values, but you can see the different values for what the optimizer uses. You can optimize. There's different ways of how you want the model to minimize, how you want it to train. So let's take a look at the accuracy and see how well we did with one value. So it got an accuracy of 0.76. So that's pretty good. It's not, I mean, it's not great, but it's pretty good for one feature. Okay, let's consider two features now. Let's consider total sulfur dioxide and citric acid and see what happens there. So this is basically the same as what I did before, except now with two features, and define the different categories, number of classes, and I can print the number of classes, which is the same in the model. And now we'll run the model again, except now with two features. And we can print the accuracy. It looks like it's the same. So it seemed in this case, it didn't make a whole lot of difference adding another feature. Now, something that I encourage you to do afterwards is to be able to try different features and run the model and see how that affects the accuracy. Try to get an idea of what features might be better to consider when you're doing your modeling. And what features might be better for being able to infer the type of wine. Okay, well, let's go do this one more time, except now let's consider 10 features. So we're going to consider these 10 features here. And so it's just the same steps that I had before, except now just more features. Okay, we'll go ahead and now we'll repeat the fit. And let's see how it changed. 0.86, so it improved. So it seems in this case, by having more features, it was able to do a better job in that case. So this is TensorFlow that's doing this in the background. And it shows that TensorFlow, it's great if you're dealing with the data set where it's complicated, it's hard to see what, just right off the bat, what features are really good to use or not, and let TensorFlow just kind of figure it out in the background. And in this case, there's still a lot of features values you need to change, but so this shows that by using 10 features, we're able to do a pretty good job. Okay, so now I'm going to actually go and use TensorFlow. So now we're going to import TensorFlow. And here I'm doing, this is a little bit more complicated than what Micheline showed in the morning, but this is also another way to be able to create a one-hot vector because in this case, when you're doing modeling with TensorFlow, you need the labels to be in terms of a one-hot vector, not in terms of just ones and zeros, as I had before. And now we're going to go and use the train test split. We can do that again. And now here we're going to set the learning rate and the batch size. So we're saying instead of training the model all at once on all the features, it's going to take a segment of that data set, and it's going to train that. And then from that, it's going to take another batch, and from what it learned from the previous batch, it's going to help it to be able to get better to fit the model. And so you can tell it what batch size that you want. A good batch size to start off with is maybe 10% of your data set. But it's a value also to experiment around with. If it's a very noisy data set, then you might want bigger batches. If it's very smooth data set, then you might want smaller batches. So that's what I'm doing here. Now, this is where it's a little funny. You'll see TensorFlow has this placeholder. So the way TensorFlow works is deals with, as the name suggests, tensors. You can have a vector is just linear, or you can have a matrix which is two-dimensional. And a tensor can be 3 or more dimensions. So it's a way of just storing. It's a way of storing data, a way of storing the data. And then TensorFlow, it uses these tensors to be able to store the data and do the modeling in a very efficient way. But what you need to do when you're creating this is you need to create placeholders, like a variable. Just where do you want to store the data? So that's what's happening here. These are, and you'll see it has this none value. And so that's just to be able to say that you want it to, for the x values, you don't know how many data points you have. You can have maybe, and so you can just say that it can have like an unlimited range. It would depend on TensorFlow itself. But we know we only want to model 10 features. So that's what this 10 is here. And it's the same here as well. We don't know how many rows there are in the labels. But we know that we have 2 here because of 2 columns. Because the first column is whether it's going to have a 1 or 0 if it's bad wine. And the second column is going to have a 1 or 0 if it's a good wine. Okay, so that's what we're setting up here, the variables. Now we're setting up the weights and the biases. Do you remember from Jen's talk where she showed how when you're fitting data and you'll have in the neural network, simple neural networks she was showing, you're going to have a value, but that value is going to have certain weight and a certain bias. And you want to be able to estimate that. It's like I mean, simple way to think about it is like with linear regression. If you're fitting a line, you're going to have a slope and you're going to have a y-intercept. And you're trying to be able to find out what are those values. Well, that's what in simplest terms, that's what these are. The weight is like your coefficients, and the b value is like the y-intercept. And that's what you want. And you're also setting up them as empty zeros. They're going to be all set to zeros in this case. And TensorFlow is going to then be able to, when it does the modeling, it's going to be able to figure out what are the weights, what are the biases, considering the data that you have, and then calculate those. And that's the model that it's producing. So here we define, those are the variables, but here we define that we want to use softmax regression. So remember back to Jen's talk. And we'll put in the x values, the features data set, the weights, and the biases. And so that's going to define our model. And now we need to define how are we going to minimize the model? How are we going to, how we want to go to be able to figure out what the minimum is for the best fit. And so here we're going to use cross entropy. And here I'm defining cross entropy as this. And now I'm going to define the optimizer using gradient descent. TensorFlow has many different optimizers that you can choose from. I'm showing gradient descent optimizer, but you can go and you can look at the documentation, encourage you to do that, to be able to see what other optimizers there are. Okay, now we've set everything else up. Now that everything is set up, we can start a TensorFlow session. So that's what's happening here. So to start a TensorFlow session, and we need to initialize the variables. So that's what's happening here. And start the session, say initialized. And so what's happening here is it's going to go through in this loop. It's going to go through, and here this is the number of batches that you're going to have. And it's just going to take, it's looping through, basically it's looping through your data set and taking off these different batches of the data set and then doing the model fitting there. And as it goes for the different epochs, it's going to tell you what the average cost is. And it's going to go through it 100 times. So that's finished the optimization. So now we can figure out the correct predictions. So now what we're interested in here, CFTF dot equal. So what we're interested in is now we've made this model and we want to compare this model with the test set. So we want to see, because we're really interested in what's the test accuracy. We want to see how well does this model infer whether it's good or bad wine, and we want to do that on the test set. So now we can figure out the accuracy using data that's completely separate from the training set. So now we're just using the test set. And we can get an accuracy of 0.7, 0.76. So you'll see it's not great. But these are something you can, but it's okay. You can, but you can keep playing around with the values, keep playing around with the learning rate, with the optimizer, and trying different values, and see if you get a better fit, or maybe it doesn't make sense to use all the features or not. But this gives you a kind of idea of what how TensorFlow works, how you can set up a model, but it requires a lot of being able to play around with different values to come up with what's the best model for the data. Now I'm going to close the TensorFlow session. So now I'm going to repeat what I just did, but I'm going to use something called TensorBoard. And so this is going to include a little bit of extra lines of code. What TensorBoard is a way of basically saving your model, saving all the steps of your model as you go through, to be able to then, at the end, load up a visual representation of your model. TensorFlow, there's a lot going on behind the scenes. And it's kind of sometimes it seems a little black boxy to understand exactly how it works. But with TensorBoard, we can get an idea. You can see visually what's going on. So now, yes. Right. Why, why TensorFlow might be better for some things than other things? Yeah, TensorFlow, it's better for things where your data is more complicated. where something maybe with like scikit-learn, it might be more difficult to be able to see, you know, what are the trends in the data? How are the features related to each other? How so if you're dealing with something where maybe if you're looking at data, it's hard to identify what the categories are specifically. In this case, more defined what the categories are, but it may be cases where it's not so obvious. Because TensorFlow, when you're giving it and you're feeding it values where the weights and the biases and the way it works is it'll be able to deal with the more complicated data set and get a model is more accurate. But you can also, you know, try different data sets and compare, or try a data set and then compare, doing with scikit-learn and then doing with TensorFlow and see what the difference is. But I think TensorFlow, it's a lot better for something where it's more complicated. So, okay. Okay, so now I'm going to go through, repeat, yeah. Right. By using more 10 features? Yeah, well, that's what, so here I was using 10 features, but you'll notice in this case, the accuracy was 0.76. So it wasn't like the 0.86 above there. This is where I'm actually using TensorFlow. There's probably other variables that you could, other things that you could tweak. There's already being done behind the scenes in the Skflow, but here where you're dealing with values that where you're in TensorFlow, we now have more control. There may be other things that you could tweak that might improve the model. Like, so one thing that I said is maybe you could change maybe try a different optimizer and see how that affects it. So, but it's, right. Oh, like which one's better to use? I think for that, I think it's probably more important. I mean, this is new, so I mean, TensorFlow is pretty new. But I would say, kind of like I said before, I think it's important to, if you're considering using TensorFlow and want to learn it, is to do the modeling both with scikit-learn and do the best that you can, and then do it with the TensorFlow and see if your model, if it improves. It may be the case, maybe TensorFlow is overkill and it doesn't make sense to use it. But as I said, I think TensorFlow is good if it's something that's more a complicated data set. But it really kind of comes down to, you know, exploring both options. I mean, I'm sure it could depend on your data set as well, which you want to use.
Actually, to add to that,
yeah.
So one of the notebooks that you would find in the repository is the OCR dataset analysis. So actually, in that we talk about this where TensorFlow does actually perform poorly when compared to scikit-learn if you don't have a lot of data to train with. So take the OCR dataset that comes with scikit-learn. It's a smaller version of the famous MINST dataset that's out there from Jan Lookup. And you actually train a TensorFlow model with it, and you will see that the accuracy you get on your final dataset is much worse compared to what you would get with scikit-learn. Now, do the reverse. Take the messier, noisier, not MINST data set that is out there, which is much larger. Try training it with scikit-learn, and you will find that it does very, very badly compared to TensorFlow. So the moral of the story, it seems to be to some extent that TensorFlow does excel when you have large amounts of data that is pretty noisy that you can train with.
Okay. Thanks, Gary. Okay. So now I'm going to define some things for TensorBoard. So TensorBoard has this thing called name scope. It's basically a way of putting certain values into a variable. So we have a name scope for the model, and also histograms for the weights and the biases in the model, and name scope for cross entropy and the optimizer, and also for the prediction and accuracy. So it's just basically what this is doing is it's saving different parts of the model to different variables. And so the TensorBoard can call those variables when it plots. So now we're going to start the session. Initialize all the variables. And run it. And close the session. So now we've created it, but now we've actually stored all of the steps. So now we can take a look at that. And I have down here, I have how you would launch TensorBoard. But it depends on your installation. So you want to launch TensorBoard from where it's installed. And you want to launch that from the directory of this notebook. And so it's going to refer to this temp directory which it creates, and this wine quality logs which it creates. And inside of that directory is it storing the file that TensorBoard needs in order to create it. Plot. So, oops, I didn't mean to do that. I'll go back here. Oh, so here, it's fine. Okay, so now I'm going to launch TensorBoard. Let's take a look at it. So now it's going to give you a link that you can open up in your browser. So we'll go back. Oops. Okay, so now it takes you to here. So from this page, if you click on accuracy, you can see how the accuracy changed. So here it's showing steps on the x-axis and accuracy on the y-axis. And you'll see in very few steps it got to the highest accuracy. So in that case, I indicate that the learning rate is quite large. It's found the accuracy very quickly. And here we can see cross entropy and see the distribution of that throughout the modeling. And there are many different things that you can explore. See histograms. You can see how the histograms of the bias and the weights. And if I can click on it, and the model. So those are the different histograms. Now, one thing also that's really neat is the graph feature. And this is where you can see how all the different parts of the model interact. So if we can zoom in, for example, we can zoom in. Here's the placeholder 1. We can see where it's doing. Here it's doing the multiplication here, matrix multiplication. And it is the gradient or gradient descent. You can click on it, and you can see how you can see that how it did the gradient descent. And then let's see, I can go back to screen. And click on train and cross entropy. And so you can zoom in on where I was doing the cross entropy. So take the mean, do the multiplication. So you can see how all of it, all the math and all of the modeling is being done behind the scenes. And you really need to, if you really want to understand it, take some time to be able to get TensorFlow board working and then really exploring all the different parts of the model to be able to understand how TensorBoard is doing everything behind the scenes. Okay. All right. That's everything. Does anyone have any questions?
Tell you like how many iterations, like how things evolved over time as the model trained?
Well, so that if you look at the histograms or the events, that's where you can see, like here, you can see how over time, how the accuracy changed, for example. But in the graph itself, this is really just showing how the modeling was done, how it was produced, but it's not showing the iterations. So, right.
Is it possible to compare two models if you have?
So what you can do is, if you go see, if I go back, you define where you want your model to be saved. So if I go, let me see here. So here's where I'm saying I want the model to be saved in temp and call and with wine quality logs. So what you could do is you could just change this to something else, and then you could compare, and you would just launch it instead of launching it as temp wine quality logs, it'd be wine quality logs 2 or whatever you want. So
I guess when you change learning rates, then maybe you'll see differences in the entropy.
Yeah, exactly. And it's really, I mean, it's kind of as I was saying at the beginning of this session that, you know, being a visual person, it's really nice to be able to have some visual tool like this where you can see what's going on. So exactly, because you can see this spits out a lot of, you can see the different steps and how the accuracy at each step is changing. But when you actually see a graph of that, then you get a better idea of what's going on. So let's see.
One thing to keep in
yeah.
mind though is that TensorFlow uses stochastic gradient descent internally while doing the optimization. So what I've noticed with some of my examples is if you don't set your initialization parameters correctly, the model will pretty much go up into La La Land pretty quickly. It will not converge.
Okay.
So suddenly you will see your accuracies like all over the place and you have nans being thrown at you. So just watch out for it. I haven't fully gotten to the bottom of it, but I've noticed in few different cases it depends on initialization where you start the gradient descent from. And given it's stochastic, I suppose it makes sense. It's something I've known.
Any more questions about TensorFlow or pandas or Skflow or maybe anything that happened in the morning or?
Now let's have the quiz.
Yeah. Oh, about the like having too big of a batch size? I didn't know. So she, right. So she was asking what the, for the, if there's a problem in some cases, if there's a batch size that's too large, and it has problems with the graphs, is that what you're asking? That I haven't had a whole lot of experience with, so I don't know. But yeah, there may be issues with if it's too big.
The problem is not with the graph itself, it's in the mathematics of gradient descent. It will not descend good enough because your sample is too diverse. Okay, so it will convert if everything else is correct, but it will take a lot of time. Okay, so you want smaller batch as each step to have a faster conversion.
Okay, thank you.
Are there any recommendations over here on what's the recommended learning rates typically?
Yes.
So, when we select the hyperparameters, is there an easy way or easy to parallel this process? Easily.
So the question is if there's a way to distribute the process to be able to pick the best hyperparameters. That I don't know if you've.
Well, no, if you use Skflow, yes, because Scikit has a way of finding the best parameter given an algorithm, but it's still local. It's not distributed. If you want to do it distributed, you can, but you have to implement it yourself, and that's like having all the possible combination or like a subset of the combination of your parameters, and then run the whole training for each combination and find which one returns the best value. Yeah, but you have to implement it yourself. There's nothing that you can run today. Just work.
And one little extra thing that I have in the repo is I made a little application using its data visualization software called Bokeh, and it has a link here. And it's sort of like D3, but with the JavaScript backend, and you can very easily produce graphs, interactive graphs. And this was just to show the different outliers and how you can pick here, different features that you want, and then you can say what threshold you want. You can go to 5, and you can see how it changes the graph. And you can zoom in on the graph or reset it. So it's a fun little tool, but it's just a way if you want to just kind of see what happens with different outliers and how choosing different thresholds affects what the graph looks like. So yeah, you can have fun with that if you want. It's there in the repo. Yes.
No. What I meant was that if you used scikit-learn and TensorFlow for training same data, you might find different results because underlying algorithms are different. Well, TensorFlow is mostly deep learning, right? what we have noticed is that when you don't have large amounts of data, TensorFlow, you will not get as good a result.
So the question in the back. Oh, you're having problems with that TensorBoard? Yeah, okay. There are some issues with TensorBoard, and it's just because I think TensorFlow is moving along very fast. So it's we try to fix this in the repo, but let me see. I think. So I wrote when I was dealing with this issue, this is something unfortunately you have to kind of figure out on your own a little bit, but this is if basically what the TensorFlow, if you've installed TensorFlow from the repo, it's for some reason in some cases it's missing two directories that TensorBoard needs in order to display it. And so what you would want to look at is wherever you install TensorBoard, it's going to be TensorFlow, and then TensorBoard, and then in the lib directory, you would want to make sure that you have two directories called CSS and JSS. And if you don't have those, I've actually put those two directories. They're in the repo. So if you download those directories and you place them in the directory of TensorBoard and then try and run it, then it might work. It still might throw an error. Let me see. Sometimes it still throws an error about a tag, but that you can ignore that as long as it displays. So if you get this, that you can navigate to here, and it gives you the URL. And if you open it and you can see it, then you're good to go. But if not, one place to check first is to make sure that you have those two directories in the lib directory of TensorBoard. So go ahead and try that. Hopefully that'll help the problems. Where am I? They're going to be in, so they're going to be, if you find where TensorFlow is installed, so you find the site packages directory, and then in there's a directory called TensorFlow. In there's a directory called TensorBoard, and below that there's a directory called lib, and you want to install it from lib. There. Right, so you want to copy those two directories there. Oh, with that in TensorFlow, just with like one feature. I haven't tried that, but yeah, go ahead and you could try that and see how it changes.
Okay, thanks a lot, David. Fabrizio wants to give a quick answer to the question previously about scikit-learn versus TensorFlow.
Mm-hmm.
So,
okay, so the main difference is in the interface, okay, in the API interface that you want to use. As we saw in the TensorBoard example, what is the you had the what's the graph?
Oh, the TensorBoard?
Yeah.
Okay.
Okay, so one of those
yeah, it's up.
Technical issues.
Fabrizio, are you talking about Skflow versus TensorFlow or scikit-learn versus
scikit-learn. First, I'm talking about the Skflow against TensorFlow. Okay, and that's an API difference. So which methods you're gonna call to get your result? And the nice thing of Skflow, as you saw, is the same interface of scikit-learn. So you can use other tools that scikit-learn has and just pass it to Skflow and they will work. Okay, so you will put like a nice layer of, you don't really know what happens inside the TensorFlow. Now, if you really want to get more detail and create models that are not being implemented by a Skflow, then you have to implement it with the TensorFlow API. And the main difference of TensorFlow APIs is in the way you construct these models. Okay, I'm going back to where we were building the raw TensorFlow model. So if you see here, we create the freeze the placeholder, then you have the variables, and then you set up the optimizers, and at some point you do this session.run. So as David says, in TensorFlow everything has to be a tensor, and the only operation to actually run it is this session.run. That will take one previously specified operation. You feed in some tensor and you get back tensors. But the real difference is in what TensorFlow construct inside. So with tools like scikit and other modeling languages, you program the tree of operation that the program has to do is embedded inside the program itself. No, it's how the parsing of the language works. While in TensorFlow you so it's implicit. While in TensorFlow is explicit. You manually construct this graphical representation, and this is what the TensorBoard is showing here. So these are nodes that are in memory, like they are actually nodes. They are not embedded inside the programming language. So they are node, and the ability of TensorFlow is to actually move these nodes on CPU, GPU, or on another complete machine. Okay, and this is very powerful because now with previous tool like scikit, you are kind of constrained in your own machine. Okay, you can share to another computer, but it's hard. Like you have to manually program it and say, okay, well, I have set up the connection, download, errors, all of that thing. Maybe the machine is another format. It's not trivial. Well, TensorFlow provides a set of interfaces that are able to communicate these tensors across machines. Okay, so this is very powerful because now you can have 1,000 machines, and if you have an algorithm that is able to scale that In that way, you can easily create a script that with one script and a proper setup of your cluster is able to run on all of those machines. Okay. Yes, this is the concept of what I wanted to, and I hope it's clearer and it's not more confusing than before. Thank you.
Thanks, Fabrizio. And Micheline had one other quick announcement as well, which is basically.
Yeah,
Okay.
if you guys did set up your data lab Jupyter Notebook using the Google Cloud platform, just make sure to shut it down, break it down.
At some point, yeah, so you don't get charged for it.
And the instructions for setting it up and breaking that down, like the whole process, I put on a link on the intro to sklearn page in the GitHub repo. So there's like a link for that if you want to know how to shut that down or sort it out.
Okay, thanks. And Olivia had a quick announcement on the Google Brain residency program, which some of you might have seen the flyer out there for. Okay.
Yeah, so if you guys, I'll just come to the microphone. If you guys liked machine learning, there are Udacity courses that do TensorFlow as well. But if you really like it and you want to spend a year doing it, we have a residency program. And basically you can apply in the fall and then you work on the Google Brain team with me and everyone else for a year, and like you could segue it into a job, or you could go do your PhD or whatever else you were doing with your life. But that's an opportunity we have. And the flyers were out there, and there's a website. I guess you can send it out if you're interested. So cool, everyone apply. Oh, also, wait, sorry. One more thing. It says on here, it says like the ideal candidate should have all this stuff, and they're actually just looking for like really varied candidates. Like you can have a PhD, some people have a high school degree, but they just are like interesting and weird. So like if you're interested in machine learning, you should apply regardless of what the requirements are.
Yeah, so apply to the Google Brain residency program. And last, Catherine has some announcements.
So first of all, I just want to say thanks to everyone for attending, and thanks a lot to our sponsor, Google. So specifically, we're being sponsored by Google Developer Relations. So what they are responsible for is the content behind developer.google.com. So you'll see a lot of them speaking at Google I/O, for example. They are advocates for third-party developers within Google, and they're also responsible for a lot of external content like documentation and outreach. So thanks a lot to them. And also, I'd highly encourage you to fill out the feedback form if you haven't done so already, because that helps us get money for future workshops, and that'd be great. So, and with that, could I have all the volunteers come up again? So I think our volunteers and our speakers did an amazing job today. So I wanted to thank, we as the organizers, we wanted to thank all of them. So first, for all the speakers, I have a little something for you guys. So, the water bottle. Thank you. Some Google swag. And then for the volunteers, I have another water bottle. There's a different kind, but you guys. Yeah, sure. Yes. Oh, blue one here. You guys can switch later. Oh yes. Like there's more here. Oh yeah. If you block us out. And then to Kendall, who is our fearless leader, you get a special water bottle. So Kendall was the one who started this, got us all together with our first Python workshop last year, which was just an intro to Python, and now we've moved on to more technical content, but I think we're definitely looking forward to holding more workshops in the future. So, did you have any other comments?
I think that's it, yeah.
Okay, great, yeah.
Okay, thanks a lot.
Thanks a lot.
Okay. Yeah.
I still think mine's cooler, David.
Yeah. Yeah, because it's clear. And I have the purple one.
No, but you can drink vodka and there's no